Okay, so before we proceed with the calculation on the example, just to explain a little bit on the relationship between some of the term that we use. So as we know that the original expression of the surface integral for the vector field is actually given by f dot ds. Okay, as I write down here. And since we know that we can this one ds is a vector form, so this one actually from the idea of the vector of the surface S is the multiplication of the unit normal vector to the surface. And in this one, how can we get this? Actually, we use the idea of for any vector form, if we can divide any unit vector form, if we can divide any vector form by its magnitude, then we can have the unit vector, right? So now, because we want to have ds, so this one vector, this one scalar, so we use this. So when we differentiate, so we have this relationship. So now we can convert f dot ds from vector to be the ds just a scalar form, where we just plug in ds is n ds, so we have f dot n ds. And then since we, as I mentioned before, in the calculation that I want to show you later on, we don't want to use the unit normal vector n, small n, so we will use the capital N, which is this one is a unit normal vector and this one is a normal vector. Okay, so as we know that the unit normal vector is given by the normal vector to its magnitude, so and then we can convert this one in this form. How can we have this? Because of as from the calculation that I show you for the scalar field before this, the formula, this one, yeah, this one, or this calculation converting from ds to dA. So actually this one is from the formula of ds is given by the normal vector or gradient f multiplied by the dA. So when we rearrange this, so we want to have only so we have ds divided by the magnitude of normal vector will give you dA. So this one can be rewritten to be ds over the magnitude of n, and this one is dA. So ds divided by normal vector, that one is dA. So that's why we can rearrange, we can rewrite the f dot n small n ds to be f dot n capital N dA. Once you have a dA, just like the surface integral for scalar field, so we can have r. So meaning that yes, in general, the surface integral for vector field is given by this one or this one, but for the calculation to get a simpler work, so we will obtain f dot n dA. Okay, so how can we get the n? So you can get the n using the gradient of the function of your surface given. Okay, so now the question is, how can we obtain the n from the sigma, the surface provided? So that is our question. The question here now is, how can we obtain the normal vector from the surface sigma provided? Okay, so for the vector field, you only use that as an integrand here or here or here, but the information from the surface is will be used to obtain the normal vector, this one. Okay, so as I mentioned before, to obtain the normal vector, you have to apply the gradient f, where this one is actually will give you a vector. You have to differentiate x for f, y, and z. Then there is a gradient of f, which is this one. So depends if your function is f, so you use f. But in this case, in more general, so let's say the what we call that, the surface equation given is phi. Okay, so then you have to find the gradient phi. Alright, so now how can we compute the n from the gradient phi? Actually, in order for you to do the calculation in obtaining the normal vector, again you have to take note on what kind of surface equation that you want to use. Okay, I'm talking about the sigma, the equation of the sigma, just like you want to evaluate the ds for the surface integral where you have a scalar field. You have to decide what kind of the surface equation that you have, right? Whether z is a function of xy, then for this your region must be on xy plane. Then for y, if you have or if you rearrange your equation of your surface function is y is a function of xy, and then you have to take note that your region will be on xy plane, and so on. Okay, so let's say these are the three cases that you have to decide before you proceed. You have to use only one of them. Okay, let's say now you are choosing that your surface function sigma is given by the function of xy. So in this case, you have to obtain a new expression where it is given by phi or phi. Some of you call this as a phi, or some of you call it as a phi. Okay. Yes, your function is f, but then you have to rearrange this to be equal to 0, which means that you have to bring the right to the left or the left to the right as long as it is equal to 0. When it is equal to 0, then you give a new name for that, where now your expression is in terms of x, y, z. And in general, we put this a new form of equation equal to 0 to be phi. Okay. And this one, if you choose y is a function of xy, so your phi will be y minus f equal to 0, and this one z minus f equal to 0. And if this is the case, then you have your phi is equal to x minus f equal to 0. That is a step 1, as I mentioned here, step 1. Okay, so why do I need to okay, I will explain this one later on. So now first you have to decide, only choose one of them, 1, 2 or 3. Okay, step 2, then you have to evaluate the gradient itself, but not f but phi, because now you have already rearranged that equal to 0. So now in this case we are not using f. It is a confusing, right? So I put phi. So phi x, phi y, phi z. Okay, so for whatever kind of or type of equation that you have here, then you have to evaluate the gradient phi. That is the second step. Okay, step 3. Step 3 is you want to okay, because now when you compute this one, so this one is actually already your n, normal vector, but you have to take note that the n here can be positive and can be negative. So what is the thing that you have to take note here? You have to make sure that, okay, the n here because from the notes that I share with you just now about the vector field here, just a second, the orientable surface, okay, so your unit normal or normal vector can be point outward and can be point inward. So it depends on the surface of depends on the sketching of your surface. So it's not always positive grade phi will be your n. Sometimes it can be negative grade phi will be your n. Okay, so what I want to say here is, yes, n is you can get n from the gradient phi, but it's not necessarily you can get the n from the positive grade phi. So I would say that your n can be negative grade phi, or it can be positive grade phi. So you have to decide which one to be your correct n, negative or positive. So how can we know this one, whether negative grade phi or positive grade phi? Depends on your sketching of the surface. Okay. So in this case, how can we know that which one to be the correct n, negative or positive gradient phi? Okay, so in order to determine that whether positive or negative gradient phi will be your n, so then I want to explain here is we look case by case. Okay, case one, which means that we have the surface which is given by z is a function of xy. Okay, so because you have z here, so we only focus on the component k. We don't bother about the ing. Okay, we just look from our calculation of the gradient phi. Okay, you calculate the gradient phi here, and then look at for the component k or z. Okay, z component or k. So positive or negative. Okay, so how can you decide that whether you have to choose k positive or k negative? So it depends on your sketching. Okay, let's say you have the hemisphere or bowl concave down, and this is your surface, open surface, yeah, open surface, and then you are given a function. So whatever function, so I just give this one in general. So then you compute for the gradient, kan? You have to have z minus f and then xy, right, equal to 0. So so this is called as phi, your new scalar function phi in terms of x, y, z, and then you compute for the gradient phi, right? So let's say I just choose a random example here. Let's say the answer is 3i minus 3 plus k. So as I mentioned before, if you have this particular equation, case 1, this equation, so we only focus the component k because we have z here. So focus on component k and look at the component k here. So we don't look at the ing, we just ignore them. Okay. Okay, now look at your sketching. So now ask yourself the n to be the n, n, this is n normal or normal vector, should be point outward to the surface, follow z positive. You just look at the z axis, right? Because this one tell you the z component. Follow the z positive or the z negative. You can see that the n always point outward to that direction, right? They are all point to that direction. So you can see the arrow here, they are always approaching to the z positive, isn't it? Z positive. You look at the arrow here. So then you can see that overall the k component should be positive. So we want the grade phi, there is a positive k. Doesn't matter the value, but the sign, we concern on the sign. We want it to be positive. Okay, from your calculation, it is already positive. So we can directly see that. So now, because this is already positive, and the positive that we are looking for, so now we accept this to be our normal vector. So we don't need to do something else. We just accept 3i minus 3 plus k is the n, which is the positive grade phi. Okay, let's say we have another example, which is a cone concave up, where we know that the formula of the cone is z equal to z equal to the square root of x squared plus y squared. Okay, so this one, the function is in terms of xy. So to get the phi, you have to find the z minus to get the phi, you have to make it equal to 0. So z minus f xy equal to 0, and this is your function phi in terms of x, y, z. And then you compute for the gradient phi. And let's say when you compute that, you get a negative 1, 2, and then 1. Okay, so now since the function here is z is a function of xy, so we only focus on the k component or z component. Okay, so you want positive or negative, so look at from your sketching. So meaning that your sketching must be correct, right? So according to your surface here, this is open surface. So what is the direction of n? So what is the sign? The sign of the z component or k component, so that we can say that the n or the capital N always point outward to the surface. So outward meaning that if you have the point here, and this is the arrow should be, and if you have the point over here and the pointing outward over here and over here, they are overall point outward, where the direction is follows the z negative, point downward, right? Outward, and looks like the value of z become negative, right? To the negative direction, down here, negative. Okay, so now we want it to be k must be negative. From the arrow here, z point downward, where point to the z, because we know that down here the z value is negative, right? So now we want it to be negative. So now look at your answer from your grade 5. It is positive, but we want it to be negative. So you will have to multiply all this gradient phi by -1, so that this one becomes negative. Okay, after you multiply all, not only this one but all, you have to multiply all terms, all vector here by -1. So you will have 1 minus 2 minus 1. So this is your n. So we accept this to be our n, which is negative grade phi. Why? Because from the sketching here, the k negative should be always point outward to the cone, follow the k negative. K negative. Hopefully you understand what I'm saying, k negative. So you can look at the arrow. The arrow is point downward of the z, where we know that down here the z is negative. So that's why we want it to be negative. We don't bother about the sign of the ing. This is only if you have this particular function. Okay. Okay, so let's see the second case. If you have a surface where given by y is a function of xz. Okay, so now in order for you to determine the n, okay, again the question is which one to be our n, negative gradient phi or positive gradient phi, which one? Okay, so let's say the function, the sigma function is given by y is a function of xz. So because you have y here, so meaning that we only focus on the y component or j. So whether j positive or j negative depends on your sketching. Okay, so let's say example 1, you have this particular shape. Okay, doesn't matter the equation. So when we want to see that the n always, we know that n is normal to the surface. So this is your surface. So let me increase. Okay, so n here always point outward. Okay, outward to the surface. Okay, outward to the surface, and follow the j, only j. Yeah, so this is why j positive or j negative, because from this direction, this arrow, the thing that we see that the n always point outward should be in this way. Okay, in this way, in this way, in this direction, and in this direction. So they are all point to the y positive. So meaning that for this particular case, the j component should be positive. So now look at from your calculation of gradient phi. Okay, let's see your calculation of gradient phi. Here I just give a random example. You compute that you have 2, 10, 1. So we want it to be positive. So it is already positive, then we can accept this directly to be the grade phi here is the n. Okay. And let's say you have another shape, another curve, another surface, but point to the other side. So n always point outward, clearly seen. This one, right? Outward. So this one inward. Okay, outward. Follow the j negative, because you can see the arrow point to the y negative. This one point to the y negative. This one y negative, and this one also y negative. So we want it, the gradient phi, there is negative sign for j. Okay, so let's say when you compute that, you have only positive, but we want it to be negative. So meaning that you have to multiply all the grade phi here by -1. So the correct n should be -2, -10, -1. So that is your n. Similarly, if your surface function of sigma is x is the function of yz, so we focus on the I component only. Okay, so let's say you have this particular surface. So when we said that n always point outward, whether capital N or small n, the direction should be outward to the surface. So in this direction, in this direction, in this direction, and in this direction always point to the I or x positive. So we want it to be positive. Okay. And this one, how about this one? Your curve is curvy and point to that way, x negative, right? So n point normal to the surface, point outward to that direction, and this one to that direction. They are always point to the x negative or I negative. Okay, so then after you decided which one to be your n, whether this or this, now you can compute the dot product between the f is given, and the n that you compute, whether from here or here. Okay, and you can have, after you have, then you can use a double integral, where this one will give you a scalar form dA over the region. Okay, so your region, whether on xy plane, xz or zy, depends on the function that you have chosen here. The same like in the surface integral for scalar field. So if you have your surface function is x, is the function of yz, so your this one, so your region or lying on yz plane and so on. Okay, and your limit should be, I mean your order of integration here should be whether dy dz or dz dy. Okay, so as I mentioned before, for surface integral for the vector field, you need extra work where you have to find the normal vector first. Where in order to get the normal vector, you have to sketch the surface, and then you have to compute the gradient phi and determine which one to be your n, whether negative or positive gradient phi. Okay, so I'm sure that you still not really can follow easily this one, but I will explain to the example. Okay, so that is a step 3, deciding this. You have to decide or find out your n. Okay, find out your n, and then after that compute the f dot n dA. So that is a step 4, and after that you can evaluate just like a normal double integral that you have learned before this. Okay, so the summary in evaluating the surface integral as I provide, so I will share with you in the e-learning for this one. So the summary of the surface integral calculation. So instead of we deal with the small n, we just directly use this one. Okay, so don't make it complicated, yeah, because it is already complicated. So we just you just set in your mind for surface integral for vector field, we use f dot n dA. Okay, but your work is to find out how to get n. Okay, so to get n, now the question is how to get n. There are three types of surface equation. Z is a function of xy, or y is a function of xz, or x is the function of yz. So for these three, if you have this one, so your region lying on xy plane. If you have this one, your region lying on xz plane. If you have this one, your region is lying on yz plane. And from there, you can determine your phi, where you have to make it equal to 0, whether you bring everything to the left or everything to the right, as long as it is equal to 0. So once you have equal to 0, then we give a new name for them. So it is called as a phi. And then now obtain the gradient phi. Okay, obtain the gradient phi. So don't forget, the gradient phi can be positive or negative sign. So how can we know that? Depends on the surface that you have. Okay, if you have this one, this particular surface, so we focus on K component. K component. Okay, focus on the K component, whether it is positive or negative. If you have this particular surface function sigma, then we focus on J component, whether it is positive or negative, depends on your surface, sketching of your surface. If you have this, then we focus only on I component, on your gradient phi. Okay, so next we look at example. How can we evaluate the surface integral for vector field?